Hi, I'm Hanson, and I'm going to talk about guesswork with quantum side information, optimal strategies, and aspects of security. This is joint work with my collaborators Vishal, Katariya, Nilanjana, Datta, and Wilde. So first I'll talk about some motivation and definitions, and then move on to our results. So the motivation will be through the Shannon entropy, which you can see is related to a guessing game. So this might be familiar to you, but I'll just go through it quickly. A game will be to guess the value of a random variable x on some alphabet, which in this example is just 1, 2, 3, 4, or 5, with binary questions. So you can ask, is x in some subset of 1, 2, 3, 4, or 5? So we might start with, is it in 1, 2, and 3? If yes, we've narrowed it down to 1, 2, and 3, and we ask, is it in 1 and 2? If no, then we know it's 3, and we're done. So the Shannon entropy is related to the minimal number of questions by this formula, where the expected number of minimal questions is smaller than the Shannon entropy, is smaller than that plus 1. And I should say in this game, I haven't written down any probabilities here. In this game, you know the probability mass function of x, right? So you would choose your subsets here accordingly. Okay. The guesswork is similarly a guessing game, but now the questions are, is x equal to 1? Is x equal to 2? And so forth. So you can only ask, they don't have to be in order, but you have to ask, is it equal to something, not is it a subset of something? So this kind of linearizes our tree that we can see here. And we actually define the guesswork as by the expected minimal number of questions. And again, you know the probability mass function, but you don't know the actual value that x is taken. And I should remark about one subtlety here is actually it's the minimal number of questions until you get a yes. So in this last case here, you knew it was 4 or 5. You ask, is it 4? You get a no. According to this definition, you'd have to ask again, is it equal to 5, and get the yes, even though you know it's equal to 5. So that's a little bit strange, but you can actually introduce a general cost for how much does it cost to ask n questions, some increasing vector of costs, and then you could just set the cost for n-1 questions and n questions to be the same. So no additional cost for the last question, so then you can kind of remove this strangeness. So I won't talk about general cost vectors here because it just adds the notation without really adding to the intuition, but I thought I should mention it. And we treat all of that in the paper. Okay. So the guesswork is how many questions of the form is x equal to x do I need to ask in order to identify the value of x. So it's a linear search instead of a binary search, and there's a very simple optimal strategy. We just ask, is x equal to x1, where x1 is the most probable element of the alphabet? If not, is x equal to x2, and so forth. And this gives us a very simple closed form expression that if p is the probability mass function of x, then we can write the guesswork as j times the probability of the jth most likely element of the alphabet. And from this, one can find that the guesswork is concave, invariant under permutations of the alphabet, and Lipschitz continuous. So you can bound the difference in the guesswork between two different random variables in terms of the total variation distance between them and the size of the alphabet. Okay. Let's introduce a more general framework, which will allow us to understand side information in this context as well. So x is our random variable on some finite alphabet, and a guessing strategy is a random variable on the Cartesian product of x with itself n times. And how it works is the player samples this guessing strategy. They obtain some g equals x1 to xn, and that's the strategy. They ask, is x equal to x1? If not, is it equal to x2? And so forth until they get a yes. And then the number of guesses when they have drawn this little g and the actual answer is x is just the minimum j such that gj is x, right? So it's how many guesses does it take until they get it right. And in this framework, we can define the guesswork as the minimum over guessing strategies of the expected number of guesses, where we have this constraint that the guessing strategies must be independent of x. And this reflects that we don't know anything about the value of x, we only know its probability mass function. So why define the guesswork in this way? Well, the assumption that G, the guessing shadow G, is independent of x is really the most restrictive assumption we can make, and we can incorporate side information by relaxing this restriction. So let's talk about guesswork with classical side information. So I've recalled the framework up here, and in this framework, the guesswork with classical side information is given by the same minimum expected number of guesses, except we allow slightly more general class of guessing strategies. In this case, the player has access to some side information y that's correlated with x, and they're allowed any guessing strategies that are independent of x conditioned on y, right? So their guessing strategy can be correlated with x through y, but not depend directly on x. And this reflects the fact that they're allowed to look at their random variable y and choose a guessing strategy accordingly. So some facts about this guesswork with classical side information. It's got a simple closed form expression, so we can reduce to deterministic guessing strategies and obtain this nice formula that's very reminiscent of the one for the conditional entropy. And it's in terms of the guesswork without side information, which we already have a closed form expression for. So that gives us an expression for g of x given y. And in 1996, Arikan established some nice entropic bounds on this quantity in terms of this 1/2 conditional entropy up arrow. So the up arrow refers to it's related to the Renyi divergence, but you maximize over part of the second slot. And it's also got a nice closed form expression, so you don't have to worry about the max. And from these two bounds, you can get that the regularized guesswork here converges to just this entropy you see on the right. Okay. So what about the guesswork with quantum side information? So in this case, Bob has access to the B half of a CQ state, classical quantum state, and he's obtained some rho bx, and he wants to guess the label. And so this might be reminiscent of the maximal guessing probability, but it ends up being a bit different because in this case we care about the expected number of guesses, not the probability of guessing it on the first try. And so let's talk about three kind of classes of strategies for achieving this, from the simplest to the most general. So the simplest would be one just performs a POVM. Bob performs a POVM on the state that he gets. He obtains an outcome, G, that actually gives him the guessing order, and then he just guesses according to this guessing order. So it's a POVM which is indexed by these guessing orders. Slightly more general would be Bob could perform a POVM with some arbitrary alphabet and obtain a random variable of measurement outcomes y, and then use that as classical side information and do a classical guesswork strategy with the side information, as we talked about in the previous slides. And then most generally, Bob could perform an adaptive sequence of quantum instruments. So applies an instrument to his state, makes a guess according to the classical outcome, and then depending on the answer, chooses the next instrument to apply. But in fact, all three classes of strategies end up being equivalent. And no matter which class of strategies you choose, you end up with the same minimal expected number of guesses. So let's talk about the simplest one, which is these what I would call ordered strategies, where Bob does a POVM which is indexed by the guessing orders. And in this case, the guesswork then you can express as a minimum over such strategies. So G is distributed where P of G given X is related to the probability of getting the measurement outcome G when the state is rho bx. So that's our usual measurement formalism. Okay, so that's our definition we've got right here of our guesswork with quantum side information, and let's discuss some things we can prove about it. So first we can get some asymptotic bounds just directly from the classical case. So I've written our bounds here. It's just like the classical one, except now we have this B measured conditional alpha Renyi entropy. So it's the same entropy we saw before, except minimized over POVMs. And the probability distribution you calculate the entropy for is related to the POVM by the same formula we saw before, except here written in terms of the joint distribution of x and y. And this B measured conditional Renyi entropy is kind of interesting. It may remind you of the measured Renyi divergence, but it's a little bit different than that. We discussed some of these subtleties in the paper. Okay, the next thing we can do is express our conditional guesswork as a semi-definite optimization problem, or SDP. So if we expand out our formula for the expected number of guesses, we end up with the expression here, which will, first what we're going to do is we'll restrict to POVMs with no repeating outcomes. So we end up with permutations pi and Sn. And the reason we can do that is that if you obtain the outcome x1, and you guess x1, the answer is no. There's no reason to guess x1 again, right? So there's no advantage to guessing the same thing twice. And so we can restrict to outcomes that don't repeat anything, and that's a permutation of the alphabet. So we end up with the SDP here, where you minimize trace of e pi, which is our POVM element indexed by permutation, times r pi, which we've written down here. So it's the number of guesses when you choose the guessing order pi, and you can actually write that nicely in terms of the permutation as pi inverse of x. So here's our SDP formulation. One thing you can do, rearranging further from this SDP formulation, is write it in terms of the joint state, rho xb times cxb, where cxb is given here and depends on the POVM. And the reason we might want to express it in this way is that we can see the guesswork explicitly as a function of the joint state here, and it's just trace against C and minimize over POVMs. And so we can see that the guesswork is a minimum of linear functions of the state, because this here is a linear function of the state, and hence is concave. And the other thing we can do with this expression is bound the infinity norm of CXB by the size of the alphabet, and end up with a Lipschitz continuity bound given down here. Okay. One other thing we can do is obtain some notion of security against an eavesdropper. So in this case, instead of x, we have a system k, which describes our key. And an ideal key is pi k tensor rho e, where e is the system held by the eavesdropper, and pi k is completely mixed. So this is ideal because if the eavesdropper has e, and it's in this tensor product state, they actually have learned nothing about the key, and they have to just guess randomly. And so in this case, it's the size of the key plus 1 over 2 gives you the conditional guesswork. So we can get some notion of robustness by considering a joint state that's close to a perfect key state, but not quite. So this is a CQ state that might have some additional correlations between the key and the state that the eavesdropper holds, but bounded by trace distance by epsilon. And we can show in that case that the conditional guesswork, so when the eavesdropper holds the quantum side information of the E part of this state, rho ke, how many guesses does it take to guess the key on average? And you end up with k over 2 times 1 minus epsilon. And what's nice here is that you still have the scaling in k obtained in the perfect case, except just with this prefactor 1 minus epsilon and missing this 1/2. And this can be a useful notion of security, because in the guesswork paradigm, we're asking how many guesses does it take to obtain the key, and that's the same kind of thing if I was entering my password into Gmail, say, right? I enter the password, I get it wrong, I guess again, I enter the password, get it wrong, guess again. I can't do a binary search like how the entropy would describe. I have to do a linear search. And so in such situations, the guesswork is a good metric to look at. Okay, let's move on to computing the guesswork. So we've seen it can be expressed as a semi-definite optimization problem, and you might have in the back of your mind, oh, those are efficiently solved by something like the ellipsoid algorithm or an interior point method, which is generally true, but the time complexity scales polynomial in the number of scalar constraints, which here is dB squared, so you just have added the POVM elements up to the identity constraint, the number of scalar variables, and then this is the problem, because we have one POVM element for every permutation, and there's n factorial permutations. And then some other quantities, like a solution tolerance, the bound and the fusible points, and so forth. And so the real difficulty here is the number of scalar variables we have is very large. So what can we do to address this to try to compute the guesswork? One thing we can do is reformulate the problem as a so-called mixed integer SDP. So that's an SDP that also has some discrete constraints, but if you drop those, you would have an SDP. And so how do we do that? So we consider extremal POVMs on this B system, and by doing so, we can realize that there exists a solution with only dB squared non-zero POVM elements. The trouble is we don't know which elements are non-zero, so we optimize over them. So this problem I've written down here is the exact same one as before, but now we only have dB squared permutations pi instead of summing over all permutations, and then we optimize over which permutations we choose. The problem here is now we have a nonlinear objective function, so it's not an SDP, and we also have these discrete constraints that these pi's have to be permutations, and the permutations don't form a convex set. It's a finite set of objects. So the first thing we can do is we can represent the permutation pi j as a binary matrix pj, and then using the fact that it's a binary matrix, we can actually do some tricks and remove the nonlinearity by adding in some extra variables. So in this reformulated problem, I won't go through here exactly how you do it. The only variables are these y, x, y, l, k, j. So now it's got 5 indices, but the indices all range over, 1 to dB, 1 to dB squared, or in x. So there's only polynomially many of these variables y. And they're subject to polynomially many constraints all written down here. So that's good. We've removed the nonlinearity at the cost of some polynomial overhead in our constraints and number of variables, but we haven't been able to remove all the discrete constraints. These PJs are permutation matrices, so their elements are all 0 and 1, and we end up with dB to the 4th binary variables. And with these binary variables, worst case, we have exponential scaling. We have to branch on each variable, is it 0 or 1, and solve a problem there. And there's different techniques to try to solve these that can work in practice, but the worst case scaling is still exponential. Another thing we can do is we can look at the dual form of the SDP. We've got an SDP, let's take the dual. This is what we get. Maximize trace of y, such that y is Hermitian, and smaller than all of these RPi matrices we've seen before in semi-definite order. So now we've only got one variable, but we now have n factorial constraints. So it's not much better, but it's kind of a nice form. And it leads us to the next algorithm, which is an active set method. So this will only get us a bound, but we can do it efficiently. So we choose some total number of constraints we wish to impose, kappa. We choose some initial y. We search over permutations. We find one such that y naught is not smaller than r pi naught. We solve the SDP imposing this constraint. We get a solution y1, and then we kind of repeat. We find a constraint that this y1 doesn't satisfy. We add that to our SDP, solve again, get a new y, and repeat until we've added kappa constraints in total. So this is an only and upper bound because we haven't imposed all n factorial constraints in general, but it can be a quite good one. And we can do this efficiently because we don't have to write down all of these RPi matrices. We could use some technique like simulated annealing or some other heuristic method to find violated constraints without having to search through all of them. Okay, and I'm actually working on some other ways to compute it, but I still don't have a polytime way yet. So in summary, the guesswork is an entropic quantity which characterizes the number of guesses required to guess the realization of a random variable. There's a simple general framework for incorporating arbitrary side information. The guesswork with quantum side information is concave and Lipschitz continuous, and we have some one-shot entropic bounds. And we have some ways to compute it, but we don't have a polytime algorithm yet. Any questions? I hear you ask, do you get an asymptotic formula for the regularized guesswork? The short answer is unfortunately we don't. We get these non-matching bounds that you can see on the slide here. All right, thanks very much.